Hello and welcome to Radio Astronomy, the podcast from the makers of BBC Sky at Night magazine. You can subscribe to the print edition of the magazine by visiting skyatnightmagazine.com or to our digital edition by visiting iTunes or Google Play.
The sheer mass of enormous cosmic objects like galaxy clusters warps space-time to the extent it can magnify light from distant objects, enabling astronomers to see them more clearly. This may sound like science fiction, but it's completely true, and it's called gravitational lensing. This episode we're speaking to Dr. David Lagattuta about a discovery made using this very technique, what it can tell us about the evolution of the universe, and the mysterious substance known as dark matter.
My name is David Lagattuta. I'm a research scientist at Durham University, and I study the nature of dark matter. I study distributions of mass in the universe and how galaxies and stars evolve over time.
Fantastic. We're going to be talking a little bit about all that today, because we're covering a pretty big discovery that you and your colleagues sort of announced, I think, towards the tail end of,
Last year, or beginning of this year, yeah, that's right.
And one of the key things about the discovery is this observational technique called gravitational lensing. So I thought it's so mind-blowing that I thought it would be worth kicking off with that. Can you give us an overview of what gravitational lensing is and why it's used by astronomers?
Sure. At the heart of it, so it says gravitational lensing, so it sort of really is lensing by gravity. But what that really means is that you have a situation where, under normal circumstances, if you're looking at a galaxy that's far away, light from that galaxy shines in all directions. A little bit gets to you, a little bit gets to your left, a little bit gets to your right. It goes all over the place. But what happens is if now you take a very massive object, say a galaxy or a galaxy cluster or something, in between you and the thing that you're interested in, then the mass of that object actually bends the fabric of space. So this is what we call space-time. It's the stuff that we all live in. And light just sort of goes on these paths in this space-time. And if it's bent, that means it will bend around it. So what ends up happening is that light that would normally a little bit gets to you, a little bit goes to the left, a little bit goes to the right, because it's sort of moving through this bent space, that light gets focused towards you. So we end up seeing more light than we normally would. And that makes the object appear brighter to us. It also makes it appear bigger to us. And so that's the concept of gravitational lensing. It really is a lens. It's making these things behind it bigger and brighter. But instead of just, a piece of glass or something like that, it's a big galaxy or something that's doing the lensing. And as the name implies, we use lensing to see things that we otherwise wouldn't see, which is what we did in this case as well.
Yes, I've heard it being described as a cosmic magnifying glass, which I think sort of works quite well.
That's right. Yeah. It's a good analogy, I think.
It sort of sounds like science fiction. And also, I think it sounds like the sort of thing that, everyone should know that exists, because it's just so crazy. It's most people would think that that's science fiction, but it's incredible, isn't it?
As a lenser, I'm certainly biased in trying to get as many people to know about the technique as I can. But yes, it is. It really does sound like science fiction. But as I sort of said, it's based in, really not simple physics, but it's relatable to things that we use and see every day. So it's a really cool technique that helps us do a lot of things.
In particular, this study that we're talking about today, which looked at galaxy cluster and then a more distant galaxy, which is known as the Dragon Arc.
That's right.
Could you give us an overview of what the study was? Why did the study pick this cluster and this galaxy in particular? What was so special about them?
Basically, the bigger the mass, the better the lens. And so there are different lenses that we know of in the universe. There are galaxies, there are stars, as we've seen, and there are clusters. Galaxy clusters, because they are so big, tend to be the best lenses out there. So galaxy clusters are, as far as we know, the largest structures that we see in the universe. And that means there's a lot of mass in them, a lot of, normal everyday mass that we interact with on a daily basis, but also a lot of dark matter as well. And so these clusters house a lot of this dark matter. And so they become really, really good lenses. And in fact, about 10 years ago or so, there was within the astronomical community an idea that we want to use these structures, we want to use these clusters, we want to find the most efficient gravitational lenses that we can. And so there were a group of 6 of them called the frontier fields. And what we had done back then was got really, really deep images of these clusters. And this cluster Abell 370 is one of those 6. So we knew already, it's one that I've studied myself a lot. And so we know that as a lens, it's really good, and we know certain structures, and we knew of the Dragon arc before. And actually, the Dragon arc itself is really quite special because it is the first lensed arc that anyone ever knew about. We had known about, so the idea, the concept of gravitational lensing had been a thing since days of Einstein in the early 1900s. For a very long time, people sort of thought, well, that's a nice idea, but we're never actually going to see anything with it. It turned out shortly after that, they used the sun as a lens, and they said, oh, this technique actually works, but maybe it's just this star. It took until about 1980, 1979 for us to see any gravitational lenses at all. And then a few years after that, in Abell 370, there was a study that they took some images of this thing, and they saw what they described at the time was an odd blue arc right in the middle of this thing. So we knew that the cluster was there, and then there was this odd blue arc. And it's really fascinating to see those old papers, the progression of, oh, this is an arc. And then a little bit later, it's like, well, maybe this is a gravitational lens, maybe it isn't. And then a little bit after that, they were able to get some spectra of the object and say, wait a minute, this thing is much further away than the cluster itself. And that was really the first thing that we saw in terms of these great arcs. So it has a really nice history, does the Dragon arc and Abell 370. And both of them are very special to me and a lot of astronomers out there.
Yeah, and that's the thing, is that, as you were sort of saying, what was once theoretical, anyone now, you can actually go onto like a search engine, type in gravitational lens, and you'll see numerous images of these arcs and sometimes rings, and that's actually the light from a distant galaxy being warped by space-time. It's absolutely incredible, isn't it?
Yeah, I love it. It's wonderful stuff. And yeah, there's so much you can do with lenses. So,
but in this instance, the ability to point that cosmic magnifying glass at that distant galaxy, it led to a discovery, didn't it?
It did, yes. We basically were able to discover some individual stars in the Dragon arc. So just for perspective again, the galaxy cluster, Abell 370, it's about 5 billion light years away, the cluster itself. So that's huge. And then the Dragon arc is another few billion light years after that. So it's about 8.5 billion light years away. When we look at galaxies that are that far away, what we're seeing is the light that's combined from all of the stars in the galaxy. So it has a distinct shape, but you're not really able to pick out individual stars all that well, simply because stars are huge compared to the average person and the planet Earth itself. But on a cosmic sense, they're really, really tiny. So if you go further away than, say, the very local universe, the idea of trying to see an individual star is really, really hard. But what we did was we used a secondary technique called microlensing. So this is also gravitational lensing, but it's a special subset of gravitational lensing that really hyper focuses a very, very tiny area. And in this case, the micro lenses that were in the Abell 370 cluster actually revealed individual stars in the Dragon arc. So we're seeing individual stars, several billion light years away, thanks to this really cool power that is gravitational lensing.
Were you just using the microlensing technique to see what you might find, or were you specifically looking for stars?
I mean, ultimately, this was a little bit of a proof of concept. We have used, astronomers have used the technique before to find a few stars here and there. Often when this is done, you can find one, maybe two in a given galaxy. But the idea here was to use the James Webb Space Telescope, which is the new, really high resolution instrument out there. And we knew based on the Dragon arc, because people had actually found a star or at similar distances in the past. And so this was a really nice test bed to say, okay, what is it that we can find? And when we did that, we ended up finding far more stars than anybody had ever thought before. We found of order 40, almost 40, 50 stars in this arc, individual stars from several billion light years away. So, and that was the wow moment, really, when you actually see these images and here are these individual points of light that after you think about it for a while, they have to be stars. That was just really spectacular. It was a really great day, a really great feeling to be part of that.
Would they have been observable without using Webb if you used Hubble, for example? And is that why you used Webb in particular?
So Webb has a number of advantages. I mean, Hubble is fantastic. It's a wonderful instrument, and Hubble and Webb together are great as well. But Webb had a few advantages here compared to previous instruments. One is that the resolution is better. So it's a bit like looking, at something really, really tiny through a standard camera versus a high def camera. So you get the resolution to say this little fuzzy blob is, if you did it with other instruments, you could say this fuzzy blob could be a star. It could be a group of stars. It could be a small patch of gas, something like that. With Webb, that uncertainty goes away. You look at it, you see it clearly, and it's like, this is a dot, which means the only thing that it can be is some kind of star. And so that was the big advantage. The other thing is that when you start to get this far away, and these stars in particular that we were looking at, they're often surrounded by a lot of dust or cosmic dust, which is, many different things. But that dust acts to obscure the stars. So this is actually, when we look even in the local universe, if we look into nebulae and things, stellar nurseries, you see it just looks like a big dark patch. And you say, well, there's a lot of stars behind it, but we can't see them. Why is that? And that's because there's so much dust because these stars are forming and creating that they scatter all the light away. And when you look at optical wavelengths, which is what our eyes see, it looks just like a big patch of dust and you can't actually see anything through it. Because Webb actually pokes through that, it looks at longer wavelengths of light, redder wavelengths, redder colors. That light is able to peer through the dust. It pierces through the dust, and you can actually start to see the individual stars themselves that are within that. And this is really what the game changer was with Webb, was that we were able to do this and see these things in this way.
Absolutely amazing. I think it's also probably worth talking about why these stars are a big deal, because if you think that the universe is 13.8 billion years old, and you're seeing those stars, effectively looking back in time, seeing those stars as they existed 8 billion years ago, does that tell you anything about sort of the early universe and even sort of stellar evolution and things like that?
It does. So we know that stars in the early universe, so right after the Big Bang, they were created and they formed and lived in a very different way to stars that we see today, like our own sun. The big reason behind that was that in the earliest days, basically the only element that was out there was hydrogen. And hydrogen is still the most prevalent element in the universe, but it was pristine. It was pure hydrogen. And so stars that formed then only had hydrogen to live in. And that made them grow and live and die in a unique way. When those first stars started dying and supernova explosions happened, they injected the universe with all of the other elements that we know. Pretty much, again, they say that we are all stardust in song and poetry alike and things like that. But it's true. That's where all of our material comes from, is from things like supernova explosions. When that happens, these new elements actually, this new material makes stars form in a slightly different way. It changes how they are created. It changes how they evolve. And so you can look at things in the early universe, you can look at things in the late universe, which is now, and understand that they're different. But the question then is, okay, how is it that these then became these over time? And so you want to try and do a time step and say, okay, we look now, then we look a few billion years later, then a few billion years after that. And where we're seeing these things is right at about the midpoint of the universe. So it's actually a pretty important anchor point in the global lives of stars, how they change, looking at the middle of the universe. It's a time period called cosmic noon. So if you start from the Big Bang, you move a little bit forward to cosmic noon to today. And cosmic noon, which is roughly when we're seeing these stars, it actually turns out that's a really important time in the universe as well. And that's because when you look again over the history of time, stars form and live and die at various rates. In the early universe, some start, and then it starts ramping up. It starts getting, there's more stars, and there's more stars, and there's more stars. When you get to cosmic noon, stars are forming like crazy over the entire universe. They're happening everywhere. It's in much, much faster rates than what they're doing now. So in fact, in the Milky Way galaxy, we maybe are creating, there's a lot of wiggle room, but let's say maybe one star a year or something like that. That's roughly what we're seeing. At cosmic noon, galaxies like the Milky Way would have been forming about 1,000 stars per year, and even more in some cases. So it's a really rapid star formation. So a lot of things are happening. A lot of things are changing very, very quickly over a short amount of time. And so that's why this particular period, it turns out, is really cool for a lot of different reasons.
What about this observation in terms of one of your key points of interest, dark matter? Presumably it can tell you a lot about that as well.
Absolutely, yes. So that's another really great thing about this. That's one thing I do want to say is that studies like this bring together astronomers from many, many different fields. So I'm mostly interested in dark matter and evolution. Many of my colleagues are interested in stellar formation and how galaxies change and things. So this by itself gave us just so many opportunities to explore so many things at once. But yes, the bit that I'm very much interested in is understanding how dark matter works and where it is and things like that. What this does is you end up seeing, okay, where are all of these stars? Where do they show up? Where do the microlensing events happen that say, okay, we get a couple of stars here, we get a couple of stars here? Depending on the density of the microlensing events, and also where they appear in the Dragon Arc itself, that tells you a little bit about, it gives you an idea about what dark matter is made of. So there's still a great debate in astronomy as to what actually dark matter is. And the real answer is we don't know. We know a few things that it's not, but there's a lot more that we don't know what it is. Different people come up with different models and say, maybe dark matter is this type of particle. Maybe it's some type of wave, something like that. Maybe it's something completely different that we don't know. So you come up with these theories and you say, okay, based on that, if dark matter is this, its distribution should be like this. We should see it here, we should see it there. And as a consequence, that means that the microlensing events have a different frequency, they have a different distribution. And right along the Dragon Arc, so the Dragon Arc, amongst gravitational lenses, and I love them all, they're all fantastic, but the Dragon Arc itself is a unique configuration. We actually even call it an exotic gravitational lens because there aren't many that do what the Dragon Arc does. And based on its orientation, you're actually really able to sample very, very closely, very precisely what a distribution of dark matter is doing along, that's making this galaxy. So this mirage, it's stretching this galaxy in ways that normally it wouldn't, and it isn't really, it's an optical illusion. You're able to use that optical illusion to see, okay, where is the dark matter that's making this mirage happen? And that's one of the things that I'm really, really fascinated in.
And so were you actually able to use the lensing effect of this galaxy cluster specific to this observation to map it more accurately or to sort of learn anything new?
It is, at least, well, we're learning a little bit, yeah. We are basically right now, and this is still work that's ongoing. So the first paper, there's hopefully going to be several more papers that are coming out of things like this. What we're really starting to understand is sub-distributions of, so when you naively think of a galaxy or a cluster or something like that. You think, okay, well, I see the stars and the gas, and they have a sort of clumpy distribution. And you kind of think that dark matter is just almost a smooth sphere or oval around these things. In reality, and we've known this for a long time, that that's not actually the case. Dark matter gets clumpy as well, and it has different shapes and things like that. But you're actually able to really start to get really, really small, really smaller masses of. So the dark matter halo that surrounds this cluster is, we think, about 10 to the 15th solar masses. So that's hugely, hugely massive. This study is able to let us see even smaller than that. So in a global scale, it's not all that small, but it's on the order of about a billion suns, or even a few 100 million suns, these distributions of dark matter, which again, to an average person is gigantically massive, rightly so. But in the universe, that actually starts to get kind of small. And it's the small things that matter, in terms of more so than the large things. They both matter, but they matter in different ways. The small things are able to let us know a little bit better what dark matter is or it isn't. We still don't know what it is exactly, but we're able to get rid of certain models or refine certain models when we look at the small things. And this is what this study is able to do with that.
Will you return to this lensing with Webb, or are there sort of future observatories and missions that you hope to return to it with?
Yeah. Well, I mean, it's a very competitive process trying to get telescope time. If we had all the telescopes in the world, that would be amazing. If everybody had one, we could do whatever we want. But we're working, unfortunately, with limited resources. But so we've put in a few proposals. We've put in a new proposal this year for James Webb. The idea with the new Webb data would be to look at the Dragon Arc for longer amount of time, and also actually with different cadences. So one of the things that came up was that, what are these things that we're seeing? Are they stars? Are they supernova? Are they variable stars? Are they things like that? And based on the data that we have, it's pretty clear that they're individual stars, not all supernova, not just variable stars. Some of them are your quote unquote garden variety stars, others are slightly different. But that was done based on a somewhat coarse time period. So actually, the way that this study worked was we took an image of the Dragon Arc, and we came back a year later and took another image, and we compared those two images, and we saw bright spots shine in certain places and then in certain other places. So you want to do that, but you want to do that a little bit faster. So you can say, okay, we can see how long these things last. We can see if it shows up in exactly the same spot, or if it moves a little bit, that means the micro lens has moved and we're actually seeing a different star. So we learn a little bit more about these stars. We actually want to use slightly different colors as well, because that can tell us more about what the stars are made of, how long they're living, also a little bit about the dust that actually they are living in. So we can use that and we can compare that to stars today that we're able to see a little bit better. So we want to do that. We've put in a proposal with Webb to try and see this over the course of the next few years. And then also we'd like to do some spectroscopy. So rather than just taking images, we'd like to take that light, put it through a prism, and see what it is that the stars are made of. So spectroscopy in this sense will tell us a little bit about the chemistry of the stars, about their ages, about what they're made of, and things like that. So there's a lot of different things. So using Webb, using the Keck telescope in Hawaii, potentially using the VLT, the Very Large Telescope in Chile, some other ones in the UK and around the world all over. There's a lot of different things. And, the future's never certain in terms of what telescope time you get, but the more you try, the better your chances of getting it. And that's what we're sort of hoping in the next couple of years to come back and revisit this. Yeah.
Fantastic. Well, I hope you do. I mean, as I said at the start of the podcast, it just feels like one of those things that everyone should know that this is a thing.
Yeah, absolutely.
So I hope you get all the observing time you want. And I look forward to hearing more about this lensing effect and discoveries, and maybe we'll get you on the podcast again in the future and chat to you again.
Absolutely. That'd be wonderful.
Thank you for listening to this episode of the Radio Astronomy Podcast from the makers of BBC Sky at Night magazine. For more of our podcasts, visit our website at skyatnightmagazine.com or head to Acast, iTunes or Spotify.